Alright, another draft physics video presentation. So this is the second in a series of 4 videos that will explain the 4 phenomenons of nature. Let's call them that, not really 4 forces. There's only one force in 2 varieties. And this is the most elemental charge, which will be the subject. This is the one that the others are just an expression of, technically, I would argue. If you understand this, the rest of them fall into place in terms of being able to understand them, in terms of this is what moves matter in the universe charge. This is the mechanism of movement for material objects. So understanding this one is a big one in terms of understanding everything else. That is photons, energy, light, and gravity, and magnetism, the big one also. Because magnetism really is just charge, just in a different configuration, but the same mechanism. So, as we will do in each of these videos, let's just rephrase, restate the basic fundamentals. There are 2 kinds of force. The forces are just made of bits, little tiny bits, and you can see that in the simulation. The idea is there's a bunch of little stuff moving the speed of light. It all moves in straight lines, okay, and it moves perpetually and forever. It never dies, and these little bits of energy, these little ball bearings, whatever you want to think of, BBs, fly through the universe, and they interact with this stuff called matter, okay, that is in 2 forms also. So there's 2 kinds of little bits. Just call them plus and minus. You can call them north and south. You can call them electron bits and proton bits. And the difference between them and these pieces of matter is that essentially these pieces of matter will react to the little bits in an inverse manner, providing the opportunity for charge and magnetism, having the 2 kinds of reaction, attraction and repulsion. So through 2 interactions, so there's 2 force bits, 2 kinds of matter, the electron, let's call this one electron for the hell of it, and the proton. This could also be distinguished as south and north, you could argue. The electron would be the north force. Excuse me. Bad night. And the proton would be the south force. That is, the north force will repel electrons. The south force will repel protons in their simplest state. It's a little more complicated when you try to mix electricity and magnetism, so I won't get into that at this moment. But anyway, so that's how you can distinguish them. And they only have 2 kinds of reactions. That is, that you can hit a proton in this case, okay, with a yellow force, can hit it with momentum at the speed of light, and what will happen is the matter bit, okay, just recognize this is, I guess I should just put, well, I could just put an M for matter. Matter is essentially, unlike this simulation, the simulation gave real mass to the matter bits, and that was sort of a mistake, because they really are like bubbles. They're much freer to move, and they move, they don't have any durable motion. They can't acquire real momentum. That is, they can't keep going in space. They can't get hit once and just keep going. But the idea is if it's hit by its same color bit, okay, then the piece of matter gets a little bit of momentum, and it will move in a direction as long as some other little bit doesn't hit it coming the opposite way. So if there's no other bit to hit it to stop it, it'll go as far as it can go, depending on how many little bits hit it. So depending on how much force it's going into, how much wind there is in one direction, this little piece of wind will keep it moving. It'll keep going until it hits something that says stop. So it's very Newtonian in that sense. It acquires a momentum, keeps it until something tells it it can't do it anymore. So there's a real concept of drag here, in the sense that if the forces were all even, you can understand that you could hit something once, it's going to go into a certain amount of extra energy by moving towards the force, and then it will stop again. Okay, so it won't have perpetual motion as the little bits do. All right. So the basic interaction is the bit goes this way, and there's a reflection, which means the little bit of energy goes back in the opposite direction. So it hits and reflects, moves this as position, some Planckish kind of distance. It's a Planck plus. If the forces are equal, the Planck will just be, a step. That'll be always the same amount. But if the forces are unequal, then it can go further. And if the forces are unequal against, it can go less distance. But there would be, in a sense, a Planck or a standard kind of amount is how you could generalize it. To just make it easier to think of, you could just think it moves this much. Each time it gets hit, it moves that much. You could just think it's in a field, and each time a little BB hits it, it moves a certain amount in that direction. So in all three dimensions, it's just getting hit and moving a Planck distance in that direction. Now that's not what actually happens, again, because if it's got a uneven field, if there's a place where the wind isn't blowing or the light isn't shining, it will move further into that space, and vice versa. If there's more coming in one direction, it won't be able to move as far in that direction. Alright, so now if it gets hit by the opposite force, this is the key ingredient. So that's pretty simple. Something goes in, reflection, a little bit of movement, and that's it. Alright, now if it gets hit by the opposite force, the difference is, okay, so the little force bit hits it, it's blue, you can see that, right? Yeah, that color's pretty close to visible. Now it's going to move, the momentum and the reflection will both come out perpendicular. Now, obviously, the perpendicular can be in and out, okay, or the perpendicular can be left and right. They're all equal from the perspective of the bit hitting the two other dimensions, going this way, going this way, going that way, going that way, are all equal from its perspective. When we're in gravity, they're not equal. But if we're not in gravity, you could sort of understand that a right turn is the same as an upturn or a downturn. So the energy goes in this way, and it will come out this way. So the reflection will be perpendicular, and the momentum will be perpendicular. That is, it's basically going to make an exchange with force going this way and this way. It's going to exchange with that force through the little bit, and so the momentum would be this way. And the rule is that wherever direction, okay, so this is a subtlety that you kind of have to understand, whatever direction the most of the opposite energy is coming from, that is, the most blue is going. If there's blue going this way, a lot of it coming at it, and there's less coming this way, then you can understand that it's going to be making an exchange with that, and the fact will be it's going to make exchanges with the place that the most energy is coming from, and so essentially you're going to end up with the reflection into the more energy and the momentum into less energy. So obviously when I mix two of these, well, not entirely obvious, but you can sort of get it. So if I mix two of these, and I'll make them small because I don't want to erase this yet, because you should focus on that a bit. So the idea is simple, that any blue energy comes from the outside gets reflected. So there's no blue in here. You get that, right? No blue. All right. There's no yellow in here. All the yellow gets reflected. So two objects, essentially, this is sort of gravity, but it's really charge. And so any yellow that comes in here doesn't get reflected. Oh, damn. So here's another little tiny piece of blue. Oh, I'm saved. I don't have to go find it. Well, it's so small, I'll probably drop it again. All right, anyway, so there's no yellow. There's no yellow force in here. So you've eliminated those two. And the real ones you have to worry about is this one going this way. So a yellow goes into a blue and goes the wrong way. That one you have to worry about. And that's one eliminated by this rule. So you don't have to worry about that either. So the basic idea is that you don't have any force in between these two in a sense, because anything that's originally trapped between them, if it's yellow, it's going to go out of the blue. And if it's blue, it's going to go out of the yellow. So you can kind of get the idea that there's a vacuum here. it becomes a very strong vacuum between the two objects. And the inverse was also true. That is, if I have two objects of the same color, you can pretty easily understand that this force that's trapped between them, that's between them in space, is going to just keep bouncing back and forth between them through the reflection process. And so the closer I bring them, the more and more they're going to repel each other, because this force is going to bounce back and forth faster and faster, and there's going to be more and more interactions on these surfaces, and there's going to be more and more pushing away from each other. And so that's all you need. You need the vacuum for the attraction, the constant reflection for the repulsion. So like two ping pong paddles with a ball that goes the same speed between them. If I bring the paddles closer together, I'm going to double the energy, because the ball is going to hit the surfaces twice as often. And obviously if the ball flies out of the paddles, you know, a red ball flies out the yellow ball, and a blue ball flies out the other one, then obviously I'm not going to have any balls between the two paddles, and I'm going to be stuck with a vacuum. And the two paddles are going to be moved into each other. So that's the essence of it. And so I'll just spend the rest of the video trying to reinforce these simple ideas. So all you have is two kinds of force. You have two kinds of matter. They inversely react to the two forces. And you have two interactions. You just have either the reflection, or you could call it just a right turn, you could call it a turn. The force turns, perpendicular, goes perpendicular. And by leaving perpendicular, it has huge consequences. So you can see that these particles, when they're flying through space, are basically doing two things. They're moving perpendicularly this way, which would end up being the same if the force is equal. You can sort of understand if the forces are equal on their sides, that they would just end up by random alone moving as much this way as they did this way as they're moving this way. And so it would all add up to nothing. But that's the two things they're doing. They're being pushed into new spaces constantly by the force. So the real thing to emphasize is they never go anywhere till a force forces them to go there. They don't have any history or life of their own. It just depends on what's hitting them at the moment. They can stop and be quiet, and they won't start again until something hits them. So it's constantly has to be fed by interaction with the field. The field tells the matter where it's going to be, sort of like the Einstein statements of, the space tells the matter. No, the field tells the matter where it's going, where it's going to be tomorrow. It all depends on what little bits are in the field. And so clearly you can understand that as, I could take a very simple system with just very few of these ingredients and throw them in space, and there's going to be a lot of action. A very neutral field is all of a sudden going to become an unneutral field, because stuff is going to hit and be flying out at frequencies out of stuff. There's going to be all kinds of changes in the color of the field. So the color of the field will go from some perfect mixture of random, yellow and blue, and in a very short time there's going to be clumps of blue, and there's going to be clumps of yellow in new orientations and new directions, and likewise there's going to be the key thing, which is bits of empty space, places where there is no force coming the other way, and the object can keep flying right into that space because of the vacuum that's possible to create. Alright, that's a pretty good start, I'd say. So maybe I will erase and reconfigure for the next segment of, for whatever the next part. I'm doing charge lines. I'm just showing the mechanism of charge. That's not the one I wanted. Yeah, it is. Close enough. Oh, it didn't work, so we'll try it again. No, it's not the right button. Okay, got it. Alright, should be back. Probably this graphic might help. I don't know, I'll put it up on the screen just to illustrate the basic mechanism. And the force comes in from one side, the momentum leaves the other side. So these are forces coming in from the sides, and the rule is that the momentum goes one way, the reflection goes the other way. It's always perpendicular to which way it came in, and it doesn't matter where on the object of the matter the force hits. So you could, just to point out a detail, just to account for these very obscure, say you could hit the thing right on its edge. Well, to the thing, to the piece of matter, it's always a perpendicular reaction. So you can only really have two kinds of interactions. You can hit something, so to speak. You can counteract something with a head-on collision, or you can counteract something with a this kind of interaction, and the two create opposite. This one creates the reflection going. It's as if, this would, you could say it goes this way and that way, but it really doesn't. It goes, the momentum goes the opposite direction, and the reflection goes this way. So anyway, so those are the two possible interactions. And so it doesn't matter where on the object I hit it, I'm always interacting theoretically with a perpendicular state, the dimensional state in this dimension, or the dimensional state in this dimension. I don't get to have a skewed interaction. You can only hit through the center of the bubble, so to speak, of matter's gravity. So you either, if I hit it here, it goes this way, so to speak. It doesn't go something like this goes this way and the force goes this way. So it's more explicit in terms of either the two kinds of interaction. Now, there could be some other subtleties that just end up counterbalancing. Just as many hit at these funny angles on both sides, so it doesn't really matter, and it all adds up to the same thing. But I'm saying for the purpose of understanding it, and frankly, it just fits the evidence better in terms of what we see in the real world. The interactions are there's only the two possible interactions. All right. So, like I said, that you have to look at the graphic for a while to get it, but the little lines inside are which way the momentum goes. The lines that go back out are showing reflections. So anyway, we'll go back to the animation because it's a little more interesting. All right, so electrons and protons in the real world. So they're basically just objects that reflect the world that comes into them. And the point being made is if energy comes in this way, you can understand that the reflection is going to be, say, this way. But that all adds up to the same thing. So it doesn't matter, if I have a whole bunch of blue arrows going in and it just reflects in all kinds of this, all these different directions, it ends up to being the same thing. That is, whatever comes in from the external world is going to be reflected back to that world. So energy is coming into the external world, and the thing the electron and proton will end up doing is changing what comes back, okay, in the sense that when they're together. So when they're a single object, if we only had one electron in the universe, you wouldn't see any change, because you'd get back essentially what came in, because for every right turn there was a left turn, for every left turn there was a right turn, for every in this way there was a one that way. So you'd end up just getting back exactly what you got in terms of a random field. But as soon as I put another one of these objects in the field, then I change all that, because you're not going to get the same universe back anymore. And now the two objects are going to interact with each other, and in interacting with each other they're going to wipe out that pattern, because they're going to be able to notice the difference in that right turn. They're going to notice where the reflections are, and they're going to notice, again, if it was another electron, what's it going to notice? So the field's hitting these two objects, what it's going to notice is that this piece of energy is now hitting it more often, because it's reflecting, constantly reflecting. So it's going to reflect a lot more than what's coming from the random field. The random field only has so much pressure. So the external universe can only create a certain amount of pressure, and that's all there is. You can't make more pressure. So obviously this can, because it's just a tiny bit of difference. So the closer I bring these two objects together, the more I'm closer than the random field's production distance, whatever you want to call it. This is obviously going to be more impetus for these two objects this one to move away and this one to move away. And so I'm going to be changing that world. Now, what happens to the blue force is even more interesting, because obviously anything blue coming in is going to be reflecting the force this way. So there's going to be a lot of more blues coming in here, because this direction is going to reflect that way, this direction is going to reflect that way, this in the dimension this way is going to reflect that way. And there's going to be a whole bunch of extra blues coming from those dimensional changes. And so now you'll have a little stream of pressure in direction, and that direction will be in all of the directions in that 180 degrees will have more stuff affecting it. So anything in this plane is going to have more blues than yellow reflections. More of the blue is going to go this way. And I don't know how to draw an anti, but let's just draw it as a box. There's going to be an absent arrow this way, and an absent arrow this way, and an absent arrow this way. There's going to be an absence of force in these directions. And so now you can understand if there's another object over here, blue one, that blue one's going to sit there and see this absence of force, because now it's not getting hit by as much blue in this direction as it is this direction. These arrows are still here. So it's still getting hit by the field, but it's not getting hit by these absent arrows. The ones that should have been here now are going this way. And so now there's going to be a vacuum here, and this blue object's going to move into the vacuum. And likewise, it's going to create a yellow vacuum for this object, and so this yellow object's going to tend to move towards this one, and that'll change this relationship. And so you can see how the dynamics will do exactly what that simulation is sort of roughly showing. It doesn't do it very perfectly, because I had some of the wrong balances established at that time, but you can see the general tendency is to the like objects repel, the dislike objects attract, and that's what this basic two interaction thing will create. That's all that's in there. Is just the rule that like I said, they do carry momentum, which is a flaw, but the rule is still the same, that the blue energy turns, the opposite energy turns perpendicular, and the same energy reflects. And those simple rules create all the attraction and repulsion you need to create all the stuff we see with charges. All right, conventional theory, I don't really want to mention in these videos. I'll mention as little of it as possible. And basically, the conventional theory is completely consistent with what I just described. That is, if Maxwell were to draw you two charges, or Faraday, they would, in the fundamental point of the argument, they would draw the charges as basically being lines of force, okay, that move very straight and perpendicular from the charge that the two charges are emanating. And the flaw is that they haven't recognized this fact that there are two different forces. So they think of it as being one force, and what they end up having is one force is coming out of one object and it's going into the other object. So they would sort of have it drawn as, this one's got in arrows and the other one's got out arrows. Now, that's just flawed reasoning. But anyway, if they were to draw them independently, generally speaking, even without any complications, just think of them as out arrows, and just recognize that there's two opposite effects. One color arrow brings you in, the other color brings you away, pushes you away, the same color. But as I pointed out, the real mechanism also includes, they're both emanating both colors. So that would be the real way to understand it. And all you're going to do is change, okay, which color they're going to reflect to the world. And so as I pointed out, they won't be reflecting any of these yellow arrows in that direction, because those are going to come out somewhere else. So there'll be extra arrows here and here for the yellow one, and the blue one would have the opposite problem. It would be creating more blue arrows going this way, and none going this way. All right. But anyway, so the point is the strength of the charge is defined by, you could understand, a distance from the object. So at a certain distance from the object, I could draw out another line and just say the amount of energy at these points would all be the same. Now, obviously, they're not going to be the same once two charges are interacting with each other, in the sense there'll be some extra of the opposite non-reflective force to the same object. So how to put that? Well, I don't think we need to go there. The difference, the point I want to make is they describe something as they call it a field line, okay? And they draw this line. This isn't a real line. Nothing, there is no line. There's no line with anything traveling this way around or doing any of that stuff. It's just a point where the length of these lines are all the same length, and you have the same amount of charge, or Q. At these, you could draw a line where there's 1 Q and 2 Q, and, you know, well, as you go further away, it'd be a half Q and then a quarter Q and all that kind of stuff. So they're just representations of the field strength. They're not representations of the actual force. So there are things that should be called lines of force, which would be these straight lines, and the field lines are these curved lines. And so you can sort of get the idea that, you know, that we're heading towards magnetism, if you think about it, just because now these lines are going to become different, okay, when we put two opposite charges next to each other. They're gonna create a difference between them that's going to create inequities here. Distance isn't going to matter anymore because now there's something else involved. Okay. Let's see how else to make this clear. So anyway, so the math is pretty much basically saying, you know, that it's actually the geometry of the math actually uses these lines and just points out that the two lines are diverging, and you can tell distance by the divergence. So this is basically the inverse square law. So you can have an R rule, you have an R squared rule, and you have an R cubed rule. The R cubed goes for the dipoles, the R squared goes for the monopoles, and the R rule is for when the things are really close to each other. And it's just basically pointing out that the force is spreading in 2 dimensions. You know, it's the divergence is in 2 dimensions from a center point. You can't help but be at different angles, the little bits. And the angle over time creates a very big distance. And if you square that distance, okay, it's a huge area. So you can sort of get that. You know, all you're doing is squaring a distance. You have this line and you just square that distance, and you can see that that opens a huge area, and that's how the force diminishes with distance. Yeah, so that's enough to say on that. So that's all perfectly consistent with conventional theory. So if we leave the drawing with just the lines of force, the drawings are accurate. So you could say where the two objects are in proximity to each other, you could understand that you could calculate exactly how much, like say if I put a yellow thing here, you could calculate how much it's pushed away, pushed towards the blue one, in the sense that there's no yellow arrows hitting it, and how much it's pushed away from the yellow because there's the reflection taking place and it's being pushed away, and you could calculate the strength of that pushing away, and you could draw a line showing its path. You know, well, its path would go in here. So you could draw this line that would show that this is how it's going to move. Now, that line, again, doesn't have anything to do with the actual force, straight force lines. So the straight force lines can create curved paths, but the force is never curved. It never moves on a curved path. Only an object can move the curved path because you're hitting it with more little BBs. So all there is for the object is a reflection of little straight lines of BBs, little vectors of BBs. And that's what the math is made of. And these curved lines emerge, okay, out of the force. They aren't the path of the force. The force doesn't move in a curved line. The force can only hit in these straight lines. So that's why there has to sort of be a more rigid understanding of the two concepts. Field lines, which you could argue is what do objects do when I put them in the field, and force lines, which are the lines that the force is actually traveling, the rays of the light bulb, for example. So this works for light bulbs. It works for all the things that are made of the elemental speed of light force. It all is straight line force, So you can understand any curved line, even the curved line of gravity, is just made of a bunch of straight line forces, okay, that are creating the curved path, duplicating the curved surface. This is perpendicular, this is perpendicular, this is perpendicular. And in a sense, the curve isn't in the force, the little bits. The curve is caused by some other aspect of the thing's existence. You can also do the simple spirograph kind of logic and understand a curved line. They do it with parabolas, and understanding orbits in circumstances where there's two objects orbiting around each other. But you can just understand that I can take 2 points and I can take a string between those 2 points, a loose string, okay, and I just have a loose string, and then I could pull that string with pressure and tighten it into 2 straight lines. And when I tighten it into 2 straight lines and move it in any direction, try to move it, it will create a curved path. But there is no curve in the force. The tension on the string are both straight line vectors, and the straight line vectors are going to create the illusion of a curve. So this would explain things like the ferrocell and all kinds of other stuff that people get deceived by. All right, so I think that's enough of that. All right, so I'll take a pause and see if there's anything else that needs to be added and such. All right, on to the subject of electricity, because charge is kind of related to it as a subject. And so now we have to understand bigger objects. So matter, you can sort of understand the protons and the electrons. And I would say size is fundamentally important in the sense of understanding that protons might be much bigger than electrons, so therefore they're moved less by any interaction. Their Planck distance of capacity to move would be less just by making them larger. But obviously electrons are easier to hit, so that gives you some reason to think electrons have to have a bigger surface area, and that protons are just materially heavier. They're just harder to move, so they move less per interaction. So you can either understand it either way, it doesn't really matter. All right, but we know we have atoms, and I would argue the atoms are held together by this charge phenomenon. And charge would tell you that there's going to be this interaction between, as soon as I put more than one electron in the system, that the electrons will be repelling each other, okay, and that they could be locked into these positions. Now, some people might just call that magnetism, and I might say that's a perfectly good analogy. You can understand this as just magnets. If I put one south side magnet in the middle, and then I put the other one's north side up, that I could create an arrangement like this, theoretically, under a piece of glass, where these can't be pushed in. They can't go where they want to go because they're being locked out of that position by the other objects, the pressure between the electrons. And so you can understand that if I try to push this one in, well, these will just compensate and push back, and so nothing goes in unless I hit it with enough force to break, to go past that halfway line of pressure. I push these far enough out this way where they can't affect this anymore, and this strength of this attraction overwhelms and takes over. But you can understand if there's a certain friction to this movement, that any movement with this object is going to create tension with the others, and therefore there's going to be a fight against it, a fight against breaking it. And so I'd argue that atoms, the 100 atoms that we consider real, are durable for this fact. They have acquired a geometry, that is a structure, where there is a great deal of balance between the attraction, the vacuum, right? So there's a vacuum between these two, and there's repulsion between these based on reflections, and that the whole system is in a tension of sorts, and it's a durable tension. It's not that easily broken. Certainly I can jiggle something enough to break something. So in atomic structure, we know we can knock an electron out now and then, and leave a gap that these others will fill. They'll come up to a new orientation that's still durable, but it's not ideal. It's not as strong. Everything is less what it is, and that's an ion. And you can have a positive ion, a negative ion. That is, I could have an extra bit in here and cause these 5 to rotate to new positions, or I can take one of the bits out and cause them to rotate to new positions. And when 2 atoms share an electron, they're really physically sharing it, would be my argument. These things aren't spinning around at tremendous speeds or any of that stuff. It's all a charge mechanism that creates very rigid geometry, durable geometry. All right, and so for those 100 configurations, it works out pretty well. If you try some new configuration, you try to add, you just can't really do it. The thing falls apart really quickly. So even with all our king's horses and all our king's men, we really can't create matter again. Obviously there are different isotopes, it's another word, of, oh, I lost the blue again. Anyway, I'll try green. There are different isotopes, where you change a number of protons and electrons in the nucleus, and you can still have a pretty good configuration. But there's really just 100 configurations, basic configurations. All right, and that's it. We didn't make any. We can't make a new atom by adding anyway that makes anything more something. Like I said, some of the isotopes become more durable than nature produces randomly, but I don't want to get into all that complex theory. So anyway, so that's the basic structure of an atom. So you would argue that if I take one of the electrons away, and I do force it to go into this new mode, that I've created a positive ion, in the sense that now the net, what does the universe see from this object? Well, I would argue that in certain places it sees a lot of negative, like really close to this electron. But, the further out you go, the more all of these things blend together and you get a net total. So the net total of this thing, even though it's a net, but it's a net spread unevenly. Okay, so it's a very uneven net produced in terms of a net configuration around the atom. But if you added it all up, it's clearly now got more positive than negative, because I have evacuated one of the balances. So the native state of an atom is to collect as much electrons as it can hold, so to speak. Like a magnet picks up so many nails, and that's how many nails it picks up. And so every atom has that kind of neutrality. It's used up all of its energy to collect electrons, and that's the way it is. And that's its native state, is that balance. I got as many electrons as I can hold, because electrons are easy to bump into, and I can grab them, just go near some other surface, and I can steal an electron anytime I want. So I can collect them pretty easily. So they tend to want to be balanced in terms of their charge. But again, the imbalance is only in one place. It's a specific kind of imbalance. And to rebalance it, say if there's only 3 here, I have to move all 3 of these objects to add a 4th one, right? So to add a 4th one, I'm going to have to redo this whole thing. So obviously I'm going to have to add that 4th one with a bit of energy. So I'm going to have a little bit of extra energy to add that 4th one back, because I have to displace the other 3 now that are arranged. So there's lots of atomic theory we go into. So the basic idea is that the electrons are on the outside, the protons are on the inside. The protons are on the inside because they don't move as much, either because of their size or because of their density, or whatever the thing is we're going to say. They're just different than electrons. So they tend to be in the quieter state, and the electrons tend to be in the more mobile state, and that's why one is chosen for the inside and one is chosen for the outside. Now, there are electrons in the nucleus, so let me point out that a neutron is basically an electron and a proton very close to each other, and we call that a neutron. We say it's neutral because it has both charges, but it isn't actually neutral, and its neutrality might be because this thing is actually spinning. In this case, the electron might be actually moving. They might be switching locations. This one's going this way and this one's going this way. And so they appear neutral all the time because they're constantly in motion. And over time, they send the same amount of energy, yellow or green, to any one location. It always ends up being the same because they constantly are switching positions. All right. So that's enough of that. So there are electrons in the nucleus. It's just that they're just holding the protons together. You can understand that if I had two protons that hated each other, okay, all I need to do to make those protons hate each other a lot less is put an electron in there, because now all this reflecting yellow force will leave through the electron, and bingo, I can bring two opposite things very close to each other by putting an opposite piece of matter between them. So I can create very close protons. So that explains the nuclear forces, which aren't really forces. They're just charge. They're just a consequence of charge. Alright, so I can have an object that has a charge, but the charge is going to be located in a place, right? So it's going to be distributed usually. So atoms can have uneven. So when I put like molecules, I can put water together and I end up with water having two different configurations of charged little bits. That has an imbalance. So there's going to be more positive at one end and one more negative on the other end, because there's going to be more electrons at one end and more protons at the other end. And so you're going to end up with a polar atom. And obviously when it's polar, that means it's basically going to start acting like a dipole. And that's a magnet actually. So it'll act like a little magnet. And obviously you can understand that one side's going to be reflecting, so you could have the energy that goes in here will come out this way, the blue, and the yellow energy that goes in here, if they were just charges, just understand they're just electrons and protons, but if I do that to an electron and proton, that's the scenario I'm going to end up with. So this end's going to reflect a lot of yellow, and then any yellow that comes into this blue is ending up going out this yellow end. So one end is going to be all yellow force, and the other end is going to be all blue force, or green, as the case may be. So yeah, you can almost see that. So again, the connection between charge and magnetism is just kind of obvious. The charges, plus and minus, the electron and proton, are in fact the magnetic monopoles. And I might as well state it just because people bring it up. There is this fact that I can't do much with a magnet to charged objects. I can't bring in a magnet next to a charged, some object that has more electrons on it. So that's the real subject here, is you can add electrons and subtract them. When you have more electrons, the object ends up reflecting more yellow, right? Then, because it's got more electrons, quite obviously. And so it acts as if it were a single electron. So the more electrons it has, the more it acts like an electron, the atom. The less electrons it has compared to its protons, the more it acts like a proton. So it's just acting like. So you can have an ion, and all you're really saying is this negative ion is acting like an electron. It's not an electron, it's not as powerful, but it's acting like one in terms of what it reflects to the world. So I can bring a regular magnet near a charge, but the problem is magnets are metallic and they acquire the charge. And so essentially what happens to the poor magnet is it gets a bunch of electrons on it, and those electrons, on the surface, the atomic substance, instead of the little magnets lining up, the little magnets all turn in the wrong direction, because now they're creating charge. They got to create electrons on the surface in higher pressure, a higher concentration of electrons. And to do that, they basically break the magnetic structure. So the magnet is broken by bringing it into a charged field. It's not that the magnet isn't affecting it, it's that the charge is affecting the magnet, essentially turning it back into a non-magnet. So you're basically demagnetizing the magnet by bringing it in an association to a charge. So it loses its charge and just becomes a regular piece of metal that will just end up with electrons on the surface and react just like any other piece of metal reacts when you bring it towards a charge, which is it becomes attractive because the electrons switch the opposite way, either too many or too little, and it breaks the magnet, clogs it. This magnet's a filter, but I don't really want to go into I already explained the filter here, so like I said, the two subjects are so tightly wound. So maybe I'll save some of the atomic stuff for the magnet discussion. But you get the idea, I think. So electricity, so let's just get that one done. kind of a simple idea. And the creation of photons. I mean, the generic general case is simple. Obviously, all of it's a bit complicated on the atomic scale. So I could argue that atoms have a neutral condition that they want to be in. So when they're next to each other in a material, they have a condition. And what happens when you hit them with electricity is that that condition changes. Okay, you're bringing in momentum in one direction, and just as I sort of explained, that's going to cause implications to the other objects. And what's going to really happen is they're going to misshape, and as they misshape, they're going to polarize. Okay, because the electrons are now going to be pushed out here, and they're going to be contracted here because you're adding pressure. So the electrons here move into each other, and the electrons here on the outside move out. And that essentially polarizes the atom. So now it's a north here and a north here, and it's a south here and a south here. And as this moves across an object, this also creates photons, but of course it creates a magnetic field in the sense that you keep changing the polarity of these atoms. Now, if you stop the electricity, you stop the magnetism, or if you just have it so they all, if you charge all of these atoms, I have to think about the difference. Now they're not moving, you know, so they're not going from one position to another position. So it's only when you're changing their position that you're changing what they reflect to the world. By changing their position, you're changing their locality to something. So say if there was an electron here, you could understand when I push that one out, I'm moving into the field, right? So the field's hitting it. I'm moving out into the field. That means I'm going to create more stuff that's going to reflect off me because I'm moving in. When I'm moving away, when I go back to my normal place, I don't hit anything. So I don't send anything to the field, right? And that's part of this whole description of how energy actually changes and changes how something else is affected by it. All right, so I don't know if I want to go too deep into too much of this as detail. So the difference between paramagnetism and established magnetism is the atoms in magnets are because the iron can actually actually already a polar atom. So like water, it's already got a side that's plus and a side that's minus, and so it just turns the atom. But in paramagnetism, the the magnetism is only temporary, in the sense that it's getting hit by more force, and it basically complements that force in the sense that if the extra force is blue, then it ends up hitting the protons, which moves them down, and it's only moving the electrons sideways. So if blue force comes in, say from the south end of a magnet, the protons move away, which makes the electrons more negative in this location, and the electrons move into the force essentially because there's more blue than yellow, blah blah blah. So they end up reflecting back to the world exactly what they get. You know, the same configuration. Push these away. Well, anyway, you know, it becomes the opposite. They're squishing the atom the opposite direction. And that's changing. Well, anyway, you don't have to think of that. Well, anyway, paramagnetism is just ends up being what the orientation you're at, which would be the blue end here and the yellow end up here, let's say. You end up creating a magnet that's exactly the same. It's going to throw back at you the same thing. So paramagnetism creates an opposite field, where ferromagnetism is complementary. That is, the yellow will point towards the blue, and therefore they'll attract, where paramagnetism creates the same kind of magnetism. So you push on, you're sending more like electron energy. Yeah, that's it. Yeah, so what you're really doing is compressing the electrons, what makes them in more tension. You end up closer to each other because you're pushing. No, it still isn't right. There's less pressure. you're pushing the electrons down. No, you're not pushing electrons down, so that's still not right. Well, anyway, I know I have that one, so we'll just, I don't know if I'll do it in this video. But anyway, I have previously explained correctly. And I want to kind of just finish up here, so I think we'll just leave it. The idea is that you're just changing the relationship between the proton and the electron and creating complementary fields, or fields that propel each other, and that's the nature of the connection between electricity, which is just force pushing electrons, and creating more pressure on electrons. And so electricity really is just, it's again another electron force. It's just another form of electron force. It's yellow force. Okay, it's pushing on electrons, or it's doing the opposite, which is extracting electrons, which is reducing the pressure on the electrons. So if you're extracting electrons, you're doing the, attracting them with a positive, then and pulling them out of the wire, or you're pushing them in and creating more pressure. And those are the only two things you got to deal with. And the reason why alternating works and DC doesn't for different applications just has to do with the fact that you have to have a changing state to actually change the field. You have to change the positions of electrons to change the field. Alright, so that's probably enough for this video. So again, charge is everything runs, if you're going to say, like I said, if you want to say one of the forces is the force, the underlying mechanism, it's that. It's the forces are moving the matter, and they move it by these rules, these two interactions. So it's charge is essentially the first essential force. Magnetism is just filtering that force that is causing all the yellow force bits to go one way and the blue force bits to go another. Electricity is just it just happens in atoms, frankly. So it's always magnetism. You could argue that's the field. You're changing how much red there is to blue or yellow is to blue. And that's always kind of a charge phenomenon, but you can call it magnetism. Yeah, I say that's, I don't know. You always get into trouble trying to name it. It's always a charge phenomenon. So a magnet does it one way, and a current in a wire does another way. That is pushing the electrons inside a material substance. Does it a different way. It polarizes the atoms the same, though. The fact is you're just changing the shape of the atoms. You change the shape of the atom, you change its polarity. You change it into, you make it into something dipolar rather than something that looks neutral. And you do it in specific directions. Alright, so, and then gravity actually has both the blue and the yellow elements, but it's really just about momentum. So in the fact that to move anything, you have to absorb the force. The force doesn't go where it's going if it hits one of these bits. And gravity is really just about hitting any bit, blue or yellow. And the reason why it's only attractive is because it has just as much blue as it does yellow, so it's not filtering anything. Alright, but I'll save more conversation on that for that video. So we'll call this one enough, and I'll see you next time. Yeah.